Okay, welcome back, everyone. You had a nice break. So today we have Patricia to tell us about geometric vertex decomposition.
Thank you for the introduction and to all of the organizers for organizing the seminar. Thank you all for being here. I will touch on a few projects, and so as collaborators come up, I'll mention explicitly who's where. I will try very hard only to use R for a polynomial ring over a field. Other rings will try to be S. I don't expect success in this endeavor and will appreciate reminders. Pay is arbitrary until I say otherwise. At a certain point, I'll want it to be C, and at a different certain point, I'll want it to be FP, but arbitrary unless I specify. All ideals that ever occur in this talk are homogeneous with respect to the standard grading. So I want to start this talk on geometric vertex decomposition by thinking about the classical setting of vertex decomposition of a simplicial complex and talk about how this gives us some algebra and geometry. So classical setting. Is a simplicial complex on n. This is the integers from 1 to n. And the Stanley Reisner correspondence is a way for us to translate between simplicial complexes and square-free monomial ideals. So simplicial complexes and square-free, otherwise known as radical, monomial ideals. And here's the rule. I1 up to ik is a face of delta if and only if xi1 product up to xik is not in the square-free monomial ideal corresponding to delta, which will denote I sub delta. We'll do an example of this at the same time that we do an example of vertex decomposition. So here is an example of a simplicial complex on 1, 2, 3, 4, 5. It's square-free monomial ideal. It is the things that are not faces, so x1, x3, x1, x5, and x2, x5. This simplicial complex is a cone over x4. This fact is reflected in x4 is just not involved in this ideal at all. So how do we do a vertex? Oh, are there questions currently? Okay, here's how we do a vertex decomposition. We're going to take first the deletion at the vertex 5. The deletion is what you would want it to be. You just erase 5. The link asks for all of the things that don't involve 5, such that when I throw back in 5, I get a face of my complex. So this is just this here together with the vertex 4 and the vertex 3. This is a simplex, and the rule for vertex decomposition is that when we get to a simplex, we declare victory. So victory along this branch. Now we'll take the deletion at 3, and the deletion, sorry, and the link at 3. Now we have 2 simplexes, and so we have victory along every branch. And so I haven't told you yet what we were checking or what the rules were for where I was allowed to vertex decompose. But the first thing that we'll think about is the win conditions. And that's when we get to a simplex along every branch. What's the rule for why I was allowed to pick 3 and why I was allowed to pick 5? It has to do with purity of the complex. So by pure, I mean that all of the maximal faces ordered by inclusion have the same dimension. So here's a thing that's not allowed. If I take, if I just straight away try to take link and deletion at 3, then what I get is deletion at 3 is this triangle together with this line segment hanging off of it. The link at 3 is actually fine. Links of good complexes are good. So the thing that's not allowed is this failure of purity, where I have one facet that's a triangle and another facet that's a line segment. And the rule is that all of the facets have to have the same dimension. So definition, vertex decomposable simplicial complex is a simplicial complex such that it's pure and there's a vertex that I can choose so that link and deletion are both pure and vertex decomposable. So it's this inductive definition and the win condition is a simplex. Okay.
Does that imply that everything you see along the way, like you know what the dimension is?
Yes. Yeah. So I haven't been precise about whether or not I'm allowing deconing, but let's say that you don't allow deconing, then link always drops dimension by 1 and deletion never drops dimension.
So that means we can't pick 4 in the beginning
Yeah.
because
So if we want to track dimension, if I impose the rule that we don't allow deconing, then you're not allowed to pick 4. Whether or not the simplicial complex is vertex decomposable, delta is vertex decomposable if and only if a cone over it is. So that's sort of a free move. So why do we care about vertex decomposition? Well, delta vertex decomposable implies that delta is shellable. This was proved by Provan and Billera in 1980 when they introduced vertex decomposability. And delta shellable implies delta Cohen Macaulay. And Reisner 74. So delta Cohen Macaulay is just a topological condition that we're checking on all of the links of delta. And why do we care that delta satisfies this topological condition? Well, delta, I'm going to abbreviate Cohen Macaulay CM from now on. Delta Cohen Macaulay implies the ring R mod I delta is Cohen Macaulay. And furthermore, if I delta is the initial ideal of J for any J, any term order, then also R mod J is Cohen Macaulay. So for me, and this is just an exercise, since I put Reisner's name here, then we take this to be a definition. You could reverse that choice. For me, I'm a commutative algebraist. Knowing who is Cohen Macaulay is just part of an essential fact about knowing the world around me. But I want us to think about Cohen Macaulayness in a few particular ways related to the varieties that I think a lot of us like. So here are just some facts about Cohen Macaulayness. So one context in which I want to think about it is intersection theory. So Sarah's intersection multiplicity. So S is going to be any regular local ring. P and Q are prime ideals. And the length as an R module of R mod P plus Q is less than infinity. Then we're going to define the intersection multiplicity, by we I mean Sarah did, of R mod P, R mod Q to be this alternating sum from 0 to infinity of -1 to the I, length of tor I, R mod P, R mod Q. When this is finite, so are all of these. And this intersection multiplicity tracks the intersection multiplicity in any context in which you have intuition. So, our rings in this talk are going to contain fields. And so this is just, I'm intersecting two varieties. I'm counting points of intersection with multiplicity. That is this number. If your ring doesn't contain a field, there are some 50-year-old open questions about how to interpret this. Where does Cohen Macaulayness come into play? So if R mod P, R mod Q are Cohen Macaulay, then this is just equal to tor 0, which is just this length. This is kind of what you would hope the multiplicity would be. And when everything in sight is Cohen Macaulay, it is. So this is a precise statement for the imprecise statement that Cohen Macaulayness is the right condition for doing intersection theory. And so a lot of what we'll talk about today is coming from a Schuberty context. So this is an intersection theory theme. And so Cohen Macaulayness is central to that kind of inquiry. Are there questions about handwriting or anything else?
S and R.
Oh, yep. Thanks. Everything is S. Everything is S. I appreciate this. Thank you. Okay.
Just one.
Anyone else?
Two more.
Two. Okay. Yeah. Okay, so Cohen Macaulayness is the right condition for doing intersection theory. We like intersection theory. Also, now we're back to honest R. R mod I delta, so this is a square free monomial ideal, is a free module over a polynomial subring if and only if R mod I delta is Cohen Macaulay. And so why do I think this should be of interest to people in this room? Why did it have a combinatorial bite? Well, in particular, it means that the Hilbert function of R mod I delta is just a constant scaling of the Hilbert function of a polynomial ring. So this was really essential in Stanley's proof of the generalization of the upper bound theorem to simplicial spheres. So that boiled down to a Hilbert function computation where you knew sort of half of it. And the other half, when it's just a scaling of a polynomial ring, you're also very happy with. So the upper bound conjecture was fix a polytope of a certain dimension with a certain number of vertices. How many faces of each dimension does it have? This should be maximized by taking the moment curve and taking your points on that curve, taking the convex hull. So this is a very combinatorial counting type of thing, and the right tool for that is Cohen Macaulay. And the last thing, that I want to say is just, it's good progress towards mile singularities. And what precisely do I mean by this? Well, suppose that your ring is Cohen Macaulay. If it's additionally regular in codimension 1, then you're already normal. If you're normal in Cohen Macaulay, then having a negative A invariant tells you that your singularities are F regular. So this is it's good for, even if you don't sort of naturally think about Cohen Macaulayness so much, it is good progress towards other properties that you probably do enjoy. So these are the ways that I want us to be thinking about Cohen Macaulayness for the remainder of the talk. Are there any questions? Okay. So here's our newer setup. So choose one of the variables of your ring. Take I, y to be xi. Write F and R as y to the d q plus r, q for quotient, r for remainder, where y to the d does not divide r and y, or sorry, any term of r, and y does not divide any term of q. So this is just highest degree in y. Set I and yx to the initial y form of f to be y to the d q. So this is what you'll get if you take a weight for a Grosvenor basis that is 1 for y and 0 for everybody else. For an ideal I in R, we're going to take NYI to be what you would want it to be, the ideal generated by all of the initial Y forms, the elements of I. We call a term order sigma Y compatible. If the initial form of F is equal to the initial form of the initial Y form of F. So this is, just picture this term order as being lexicographic, and your first variable is Y, and you don't care what happens after that. Let's see. So, well, fix a Y compatible term order less than right. CYI is going to be NYI colon Y, and NYI is going to be NYI plus Y But then we want, sorry, maybe I just want to say this. NYI plus Y is going to be this. NYI is going to be the ideal that doesn't involve any of the Y's. So you can take this and intersect it back to the ring where Y is no longer a variable. We'll give explicit generators for these in a second.
Term order is more compatible, that's true for odd.
Yes, thank you. Left is fine. What you really care about is just that the initial scheme of the scheme you started with should be obtained by taking initial scheme with respect to the term order that's one and then a bunch of zeros, and then putting on your ideal.
Patricia,
Yeah.
could you recall the definition for the colon notation?
Oh, yeah, great question. So IJ is
Could you reach a little higher?
Everything that knocks J into I. So in particular, I is always in I colon anything. Okay, so if NYI is equal to CYI intersect NYI plus Y, we call this equality a geometric vertex decomposition of I at Y. Fact, this equality holds if and only if I has a generating set that is linear in Y. So if I have a generating set where none of the generators have any term divisible by Y squared, then you take that and it will give rise to this equality. And we'll maybe see that in a second when we give a Grosvenor basis definition of this. So if I admits a Grosvenor basis of the form y q1 plus r1, y qk plus rk, h1, hl. No y's where you don't see them. So y does not divide any term of q, I, ri, or hi. Then CYI is equal to Q1 up to QK, H1 up to HL, and NYI is equal to H1 up to HL. So if you have a generating set of this form, then doing the figure on a Y-compatible term order will give you a Grosvenor basis of this form. And then once you have these, then this equality is clear. So Knutson, Miller, and Yong introduced this in the study of vexillary matrix Schubert varieties. And they showed, for example, that if you start with a Grosvenor basis, then these are also Grosvenor bases of the ideals they generate. And also, just a note that NYI in this case can also be written as Y CYI plus NY. So these equalities give us a lot of short exact sequences. We track the Hilbert function, we track invariants. This is a lot of information on tracking, for example, the A invariant and the degree, and just more generally the Hilbert function. So Castellani Mumford regularity you'll also get out of this.
So would you saying that if my Grosvenor basis is square free, then these will be square free and you can keep going?
So these don't involve Y at all.
Yeah.
And so you would need to pick a new variable and hope that you're square free in that variable.
Do the H's belong to the C's because they're both in the H's and the N's? The way you wrote it there, you're getting a Y. You're getting but in the next thing over, you got a Y, CYI. So it looks like you're getting Y times the H's in there.
Yeah, and then I don't actually need those as generators because I also have N.
Okay, so,
And so-
I was just wondering if the H's were, why the H's were in both.
So N is contained in C. And one reason why this should feel good to us is that the link, when I do a vertex decomposition, the simplicial complex that is the link is contained in the deletion. And the ideal situation is order reversing. So link contained in deletion is ideal of deletion contained in ideal of link. This generalizes that. So we have ideal of deletion, which this will be contained in the ideal of the link. Often you don't have to write these H's. We'll get them for free sometimes. So let's go ahead and name this link and name this deletion. All right, so why are these reasonable names? Why would we study this? Oh, first I need a definition, which I guess I didn't. So we say that the unmixed ideal I, unmixed means V of I equidimensional. And no embedded primes. So all of the associated primes have the same height. So we say that the unmixed ideal I is geometrically vertex decomposable. Is it okay if I just write GVD? If either I equals 0 or I is 1 or I is generated by variables, or if there exists a variable so that CYI, xi, I, and N xii are geometrically vertex decomposable in K adjoint x1, xi caps. This means I'm omitting xi up to xn. So this is a recursive definition that mirrors the definition that we have at least allowed for a vertex decomposition, where you choose a vertex, you split into link and deletion, you win if you have a simplex. The analog of having a simplex is one of these. Or if you can decompose and keep going.
C and N being unmixed is part of the requirement?
Yes, yes. So yeah, I guess that. And there, in the same way that there is a non-pure version of vertex decomposable, there is a non-pure version of this theory. But this definition was meant to be, I start unmixed, I decompose. In order for these to qualify to be vertex decomposable, they have to be unmixed.
For this fact, the fact does not imply it's,
No. This tells us we can go one step.
but it doesn't even imply it's unmixed.
No. You can have this, you can have a vertex decomposition that, so here's a small example. So let's take J to be YX, YZ. Then. Sorry, is it? YX, YZ. NYJ, well, I mean, this just is the same thing. It's a monomial ideal. And it breaks up as XZ is the link. And there's nothing in the deletion, and so we just get this Y that's the plus Y. So here it is having a prime of height 2 and a prime of height 1. So just being able to get this equality is not saying anything about unmixedness. That's a real assumption that you have to make on the ideals you're considering for the following theorem to be true. Worse theorems are true in the possibly mixed setting. If I is geometrically vertex decomposable, then I is radical and Cohen Macaulay. So Cohen Macaulay implies unmixed. If we don't have unmixed, then certainly this theorem can't be true. So this is mirroring the vertex decomposition set. So we say that a geometric vertex decomposition is non-degenerate. If CYI is not the unit ideal and the radicals of CYI and NYI don't agree. If I is radical, then this can only happen this case is if Y minus something is a generator of your ideal. So you should think about this as Y is in your ideal. So this should be like you have a simplicial complex where you have a vertex that you just didn't use, but it was in your ambient set. And this is deconing. So this is your variable just isn't in your ideal at all. So if R mod I is equidimensional, and admits a non-degenerate geometric vertex decomposition, then R mod CYI is equidimensional, and the codimension of I is equal to the codimension of C, which is the codimension of N plus 1. So these are the heights that you would expect for these ideals in a vertex decomposition of a simplicial complex. Yes.
I have a question just so I can put this all in perspective.
Yeah.
So if we start with a simplicial complex and take the Stanley Reisner ideal, can we always vertex decompose all the way down to the win condition?
No, so some simplicial complexes are just not vertex decomposable. So in particular, we know that vertex decomposable implies Cohen Macaulay implies equidimensional, which is, so that's a class of them that won't be, but here is a small example of something that, well, I mean, one thing is just we said that it had to be equidimensional. So here's an example where it's not, and so this is certainly not vertex decomposable. But here is something that is equidimensional, but it is still not vertex decomposable. And so the problem here is that wherever you vertex decompose at the next step, you're getting something that is not equidimensional.
Are there simple conditions you can put on the simplicial complex that guarantee this?
There are obstructions to shellability. And if you're not shellable, you're not vertex decomposable. So there are just a couple of subcomplexes that you can't contain. For vertex decomposition, there isn't a characterization of that form. Okay, good question. Let's see. Okay, the next thing maybe I'll just say aloud, which is that geometric vertex decomposition has a second life over in the theory of Gorenstein liaison, and there's a lot of good work over there, particularly by Uwe Nagel, that relates resolution, so a resolution of type E or type N, if that means something to you, and if it doesn't, just some resolutions, where you can port over a resolution from I to C or vice versa. So in that setting, I and C look much more symmetric than they do here. All right, so examples. So example 0. Just the Stanley Reisner case. So a Stanley Reisner ideal is geometrically vertex decomposable if and only if delta is vertex decomposable. So this does recover that theory. Example 1, maximal minors of a generic matrix. So we want to take the ideal that is generated by the size 3 minors of this matrix. The natural generating set is a Grosvenor basis. It's a universal Grosvenor basis. So in particular, it's one with respect to x35 being largest. So let's think about how we're getting the link and deletion. Deletion means I want all of the generators that do not involve x35, because I'm taking maximal minors. If I don't involve x35, I don't involve this column at all. So this is just the size 3 minors of this 3x4 matrix. The link is saying, well, first of all, I have to get all of the deletion. We'll handle that in a second. But sort of the YQI plus R, the interesting part is saying, I want to take all of the generators that do involve x35. So maybe we'll pick on this determinant coming from the first Q column. And I want to take the multiple of x35. So that is a 2x2 minor that lives in here. In particular, when I chose the first 2 columns, it's this 2x2 minor. So I'm getting all of the size 2 minors that live in here. This is a case where I don't have to write those pesky H's, because if I am a size 3 minor that lives in here, I am in the ideal already generated by the size 2 minors in here. So for the case of maximal minors, this is a very clean description of link and deletion. If you don't like this, you won't like anything that happens for the rest of the talk. So what questions are there on this?
Why does the deletion algebraically means passing to H? No.
So the deletion means I'm taking.
Passing to it.
Yes. So all of my Grosvenor generators that just don't involve a Y. So this is n x35 I, if I I is the ideal generated by these minors. And this is C, x3, 5, I. Going again, link here is I'm picking on x3 for now, so I'm size 2 minors, 1 box smaller. And the deletion tells me don't use this column, and so now I'm down to 1 determinant, and I keep going. A very clean thing about this setup is that link followed by deletion commutes with deletion followed by link at appropriate places. This does not happen in general. This example is a very, very friendly breakdown of link and deletion. To check to see if we've won, well, we need all of the ideals showing up to be height unmixed. And that's true because all matchable minors of generic matrices give me height unmixed ideals. This is a fact we already know. Or we could actually get some of the setups up in a different way. And we look at each of the leaves and we see that either we're the 0 ideal, the unit ideal, or an ideal generated by variables. And so in this example, this is geometrically vertex decomposable. More generally, all ladder determinantal ideals are geometrically vertex decomposable, and you just have to make your inductive set larger to get it.
On the left,
Yeah,
is that really only 1 step, or do you have to do 2 steps? Or delete the.
when I take the deletion here, this is saying, so this is a principal ideal.
3 by 3
This-
minors.
Yeah. So 3 by 3 minors of a 3 by 3 matrix is just the 1 generator. And so to take deletion, we say, what are all of the generators that don't involve x33? And there are none of them. Good question. Other questions? Yeah.
I think I'm confused about the language for going all the way down versus just going 1 step. So.
So a geometric vertex decomposition is 1 time when this equality
Yes.
holds. And we say that an ideal is geometrically vertex decomposable if the whole tree is good.
Thank you. And this GVD in this definition, which one is it?
Geometrically vertex decomposable. Yeah, so I am using the 3 letters to mean both is a geometric vertex decomposition. It also is geometrically
And
vertex
then in
decomposable.
this definition, then you are also requiring that sort of recursively all the way down.
Yes,
Okay, so C and N then are also,
geometrically vertex decomposable. Yeah,
yes, got it, thank you.
good question. Other things to notice here are that the heights of the ideal don't change when we take a step in the direction of the link. The heights of the ideal go down by exactly 1 when we take a step in the deletion. And if we remember our formulas for heights of determinantal ideals, we can check that directly here. Other questions on that example? Okay, the next 2 examples are more combinatorial, and I hope that one of the next 2 examples appeals to you. So a fact about geometrically vertex decomposable ideals is that you can have a geometrically vertex decomposable ideal that has no square-free initial ideals. So it is not just our usual strategy of first go to the initial ideal and then decompose, maybe just doesn't work. Maybe there aren't any square-free initial ideals. And so in that sense, this covers more ideals. This is not actually the thing about it that I find most helpful. Those examples I'm not aware of occurring in nature, though you can write them down. A thing that does happen for me in nature is that I have an ideal that's defined combinatorially. It's defined, based on combinatorial information. And if I go all the way to the initial ideal, I can no longer see enough of the combinatorics to understand the ideal. So I don't know sort of which monomials are coming from where. I don't know how I should be taking my next step in a vertex decomposition, even if I do end up with a square-free monomial ideal. And this procedure of going step by step, of going just 1 variable at a time, it preserves more of the defining combinatorics. And so I can tell more easily what's going on. And this is an example of actually both of those situations, because we don't, in the term orders we'll talk about in general, end up with square-free initial ideals. And sort of more importantly, I really can't tell what's going on if I go all the way to the initial ideal in 1 step, in 1 fell swoop. But in 1 step, we can see it. So let's talk about Schubert determinantal ideals, which were introduced by Fulton in '92. These are affine varieties, matrix Schubert varieties are, they live over Schubert varieties in the complete flag variety, and they remember a lot of information about Schubert varieties. So we're going to talk about today, we're going to talk about taking a geometric vertex decomposition at Z33 of this one Schubert determinantal ideal. I'll tell you very quickly how we get this ideal from this permutation and one-line notation. Schubert determinantal ideals are indexed by permutations. Here's how you get an ideal. Take your permutation, write down the permutation matrix. From the permutation matrix, our rule is that we send out death rays down and to the right. And we look at, these are coming from Borel, actually, this is not sort of just a random thing. We look at the squares that are not crossed out. These are the diagram. They record the Coxeter length of the permutation, the number of these boxes. Stand on any one of these boxes. Look northwest and count the ones. So here I count 0. This tells me to be rank 0 in a generic matrix in the 1 by 1 corner. So how do I be rank 0? Well, it's if that one entry is in my ideal. If I stand on this square, I look northwest, I see 2 dots, and that means that in a 3 by 3 box, I have to be rank at most 2. How do I force a matrix to be rank at most 2? I send the 3 by 3 minors to 0. So this is the 3 by 3 minor there. If you haven't seen Schubert determinantal ideals before, that was surely too fast. And the sort of takeaway is that these are determinantal ideals coming naturally from combinatorial information.
This is the defining equation of the matrix Schubert.
Yes, these are defining equations of matrix Schubert varieties. Matrix Schubert varieties are take your Schubert variety in G mod B, just lift back up to G, inject G into n by n matrices, take Zariski closure in there. So that's the sense in which they live over Schubert varieties. And Fulton showed that these are defining equations. So we take our geometric vertex decomposition here. And just by writing down generators, we could compute that it's this particular monomial ideal, it turns out already here. This monomial ideal is coming as an intersection where this is the link. So this is C33I, and this is NC33I. I is 2143. And here's how we're going to get these permutations. We get them by looking at Lamley and Shimazona's bumpless pipe dreams. So every permutation is attached to a set of bumpless pipe dreams. Those are diagrams that look like this. And I won't define them, but they're tilings of a grid subject to certain rules. Starting from the row to bumpless pipe dream, we can get to any of the other bumpless pipe dreams for a permutation by performing droop moves. So a droop move is I take this wire and I droop it into an available square. In this case, there are 2 droop moves that I can perform. I can take this wire and droop it down here, and then I get this bumpless pipe dream. Or I can take this pipe and I droop it down here, and that gives me this bumpless pipe dream.
What is the word droop?
Droop, like if you have like a droopy sad face, then it's, you're walking around like this, and so or yes.
Do says I'm happy.
Yeah. So yeah, a droop is anything that's sort of floppy like this, but it has a rather sad connotation.
How do you spell it?
Oh, DROOP. And if you want to learn more about why these are named droop moves or why these are named bumpless pipe dreams, ask Thomas Lamb the next time he's around. It's his fault. So we're stepping through these combinatorics. We start with the row to bumpless pipe dream. We perform all allowable droop moves. We can take any of these drooped pictures, and just by straightening out the pipes, we get back a row to bumpless pipe dream for a different permutation. And if we fix one of these southeast corners and we consider all of the allowable Drude moves into that corner, we get two permutation, or in this case two, but we get some finite family of permutations of the same Coxeter length. Their intersection is the link. And then we get one permutation that comes from, suppose I didn't use that box at all. Because if I didn't use that box at all, I can cancel it by multiplying by a transposition. And then I get a permutation of shorter Coxeter length. And so the upshot, what I want you to take away from this picture is that a geometric vertex decomposition is reflected in natural moves on the combinatorial objects. So Drude moves are the way to step through the bumpless pipe dreams and get stuff that's smaller, either smaller Coxeter length or my blank boxes are bubbling up northwest, getting me closer to a monomial ideal. And this is also in the algebra and geometry part of my flat deformation. So what this allows us to do is count the top dimensional components of the initial scheme, which may not be reduced. We count them with scheme theoretic multiplicity, and these correspond to the bumpless pipe dreams for the permutation W. And so this is for term orders where I'm always going to pick a box to be a box in this corner, so southeast, to be biggest at the next step.
We get some terms in the Grothendieck over here, but
Great question. So to do this, we have to throw away the embedded components at every step. And this is a real loss. And this is sort of unmixedness we can fix in certain ways if we have to, but embedded components we really can't, this theory doesn't cover it. And this is a thing I hope to get to. I have 8 minutes, I will move quickly. So this is a theory that does homology really well, the straps. So these bumpless pipe dreams are giving you the multi-degree, so these are giving you the Schubert, double Schubert polynomials, but they're not giving you the Grothendieck polynomial, which is the K theory. Okay, the last example is defining ideals of Schubert varieties of pairs of linear spaces. So these are things that Andy and Alex are thinking about in the context of David Spire's F-vector conjecture. And this is a generalization of Schubert varieties of a linear space that most people in this room know more about than I do. So this is from, certainly June Cannon has tell us about this, as can Botong. And also Connor here. Yeah. So other, these are growing out of that very important work. So here's what we're going to do. We're going to take two linear spaces. They realize two matroids. And the ideal is coming from determinants of a bunch of square matrices that are coming about from circuit equations. So we're taking a subset of the columns of these matrices. And when the size comes from this sum of ranks, then we throw that determinant into our ideal. But what is this variety? Well, it's the closure of this thing in Cn cross C. These ideals are geometrically vertex decomposable. So Federico and Adam, when they, long ago, they gave shellings of the one linear space version. And so any vertex decomposition gives you a shelling. And so this sort of recovers that result that they're shellable and also gives this other result in these more this more general setting. So here again, my claim is that the geometric vertex decomposition naturally reflects the combinatorics of the situation. So specifically, the way that I'm getting the ideal of the deletion is by taking a deletion at the final column in both of these matrices, realizing my matrix. And to get the link, I get the ideal of the deletion plus what I get when I take a contraction at the final column in one of these matrices. And this is fine whenever, sorry, so this should be M1, when the rank is greater than 0. So here's an example with equations of this happening. So here is U24 when L1 is just the all ones vector. Then this returns us to the case of just one linear space. Here are the equations. Here are what the equations look like for that definition on the board that's now hidden. And here we are getting the deletion just by chopping off the final column of our matrix. And we take the link by taking a contraction. This matrix is written so that I already have a 1 here. And so my contraction is this operation. So this is the geometric vertex decomposition reflecting steps in the combinatorics. Done with examples. I have 4 minutes, which means I will not tell you, I will not write down things about Frobenius splitting, but I will tell you some things about Frobenius splitting. So Frobenius, the Frobenius map is the P's power map. We do this in characteristic P. It is injective if your ring is reduced, which means that it at least has a set theoretic inverse. We're interested in module maps that are inverses. If the coordinate ring of a projective variety is Frobenius split, then this looks more like something in characteristic 0. Specifically, I mean, you get Kodaira vanishing, which is usually a main loss when you go to characteristic P. Alan Knutson did a lot of work on Frobenius splitting in this sort of Grobnery context. And there the theorem is, suppose I have a homogeneous polynomial of degree n, and the leading term is the product of the variables. This gives me a splitting of affine space that also compatibly splits any of the components of my hypersurface coming from this polynomial f. It also splits any intersections of those components, and then components of any of those intersections, and so on. And so we get this poset coming from intersect, decompose, starting from the components of f. If we have a geometric vertex decomposition, then taking the initial y form of this polynomial f induces a Frobenius splitting on the varieties coming from link and deletion. And work by the remaining authors who haven't yet shown up here, and that's in progress, is you can sometimes reverse this. So with some additional hypotheses on the splitting, you can take something that compatibly splits link and deletion and pull it back up to a splitting of I. So this is realizing some more of this symmetry that we would sort of hope for. So I want to, in 2 minutes, tell you some questions. Let me take my list so that I don't forget things. Okay, here are some things that I don't understand, and one of them comes from Leonardo's question. Is this theory is good for cohomology? It's really terrible for K-theory. We just have to throw away that information. So is this a special case of a thing that should be interpreted? Is there something out there that gives us this partial Grosvenor deformation, but also retains information about the K-theory? Is there a Reisner's criterion for geometric vertex decomposition? If you have a simplicial complex, you look at all of the links, and the topology of all of the links tells you whether or not your simplicial complex as a whole is Cohen Macaulay. I don't know if there's information that I can get from looking at all of the geometric links. Does embedding into a really high PN improve the situation? Often embedding into a really high PN improves situations. Specifically, why I think this is true, or why I hope this is true, is by looking at the case of toric varieties. So we know that if we, by work of Gaku-Liu, if we take a sufficiently high dilation of a polytope, then you get a regular unimodular triangulation, which he hopes is vertex decomposable, he says, but also he doesn't really think about vertex decomposition. But if this is vertex decomposable, then what you're getting is a vertex decomposition of a square-free initial ideal of this re-embedding of your toric variety. And so this is an entry point for taking your varieties and embedding them higher, hoping that geometric vertex decomposition goes well. There's a really lovely theorem of Conca and Barbaro that tells you that if you have a homogeneous ideal and it's Cohen Macaulay, then its initial ideal is Cohen Macaulay. This is a really hard theorem. It uses a lot about square-free initial ideals. A thing that I don't know is suppose I have a Cohen Macaulay ideal and I look at NYI. Suppose NYI is radical, so I'm not going all the way to an initial ideal. Is that necessarily Cohen Macaulay? If it doesn't have any Cohen Macaulay initial ideals, then I don't get to use Conca-Barbaro. And it would require a really new argument to say, does this one-step degeneration go as well as going sort of all the way to a monomial ideal? And the last question is, how does geometric vertex decomposition play with singularity theory? And I mean that pretty broadly, because we do know that it does something good for F splittings. But we don't know, there are a bunch of other F adjective words. And we don't know, so, F regular, strongly F regular, F rational. I don't know that there's been any work on those. I also don't know about these characteristic zero things like log canonical threshold, or that you might think of as close to interpreting F splitting in characteristic P. So I think those are, people who think about Grobner theory and people who think about singularities don't have so much overlap as a community. And so my impression is that people just haven't really thought about geometric vertex decomposition in the context of singularities, but the F splitting looks to me like there's some hope for something there. So with that list of many things I don't know, I apologize for keeping you from cookies, and I'll end there.
So this comment you made about around the fact, if I have a Lex term order and I have a square-free Grobner basis, then it's like the only thing I have to worry about that at some point it becomes not equidimensional.
Yes. Yeah. And I mean, also in a vertex decomposition of a monomial ideal, the only thing you're ever worried about is that a deletion is not equidimensional, because links of equidimensional complexes are equidimensional.
So this vertex decomposability preserves Frobenius splitting.
Yes.
So
The kind of Frobenius splitting that is trace of F, this homogeneous F, where the initial term is product of the variables.
so can you go backwards?
Sometimes. So here's the situation in which we know this is a work in progress with Elisa Gorla, Jenna Rajkat, Mayada Shahada, Lisa Saccia, and Emanuela De Negri. And so we can go backwards if the ideal of the deletion n is Cohen Macaulay and Gorenstein in codimension 0. And if there is a factor of F that is in C but not in N. And this is coming from the Gorenstein liaison theory, how you do the lift. So that's where the G0 condition is coming from. It's you need it to get Hartford's generalized theory of divisors to work.
If instead of taking CYI, I take like the saturation, what changes?
It's saturated.
Why?
Well, it's a homogeneous prime ideal that is not the maximal ideal. Are you saturating against something that's not
Saturating against
the...
like why to the infinity?
Oh, I think I'm saturating against the maximal ideal. So CYI already doesn't involve Y. So saturating doesn't do anything, but if you want to take the initial.
I want to change the definition of CYI so that instead of NYI, I put a Y to the infinity.
Yeah, so in general, in general, I guess I should have done that. In this case of geometric vertex decomposition, because you're linear in Y, coloning by 1Y is the same as saturating against Y.
So if like, let's say I'm not linear in Y.
Then I should have defined that to be the saturation, and I apologize. Sorry, this is what you should do. And once you're here, it's the same. Thank you.
Is it true that like this will never be true if it's not linear?
That's right. Yeah. So
even with the production.
Yeah, so that intersection on the right. You can, well, so the product is linear in Y. And the product and intersection are the same up to radical. So if I'm already linear in Y in the product, then I can't get more powers of Y by taking radical, which gets me the intersection.
Okay.
So the right-hand side is definitely linear in Y, and so it can only be equal to the left-hand side if the left-hand side is linear in Y also.
Okay, I see.
Question.
What's the picture we should have in mind for this one-step degeneration?
So how do you picture your Grosvenor degenerations in general?
I can ask you that as well.
So I can only picture them when they're small, but so here's how are we done recording? I hope so. So here's how I picture xy minus z squared. And then one of my Grosvenor degenerations is getting me, I deform sort of slowly until I get a union of planes. And my other Grosvenor degeneration is getting me the xy plane twice. And so I picture this motion where I have my variety, and then I'm just sort of scaling along an axis. So I pick one of the axes, that's my y, and I just stretch by it.
Which one is the deletion and which one is the link?
So in this picture, one of these planes is the deletion plus y, and the other one is the link. So the deletion plus y and the link are each giving me, the deletion is, if I start with one component, the deletion is one component, and the link is a union of components. And so I'm picturing this deformation as going to the ideal of the initial y form. And then one of these components is the deletion, and all of the rest of them are for the link. Is that helpful or unhelpful? I can't say less. I could say more, or I could leave it. So I stretch around to get to NYI. One of the components is the deletion. Whatever is left, that union of components is the link. And if I start equidimensional, I end equidimensional.
Any other questions? If not, I think Patricia.